All right, welcome back to the deep dive. Today we're jumping into something really specific, but super important in, how computers actually work at speed. We've got a whole stack of sources here, technical papers, articles, all about PCIe retimers.
Yeah, so our goal is pretty straightforward to figure out what these things are, what problem they're actually solving. It's kind of fundamental physics, really, and, well, why they're suddenly everywhere, from your PC to these huge AI data centers.
Absolutely. It's a fascinating area because, honestly, as things get faster, and data rates are just climbing like crazy, right? Gigabits, tens of gigabits, hundreds now, just getting that signal cleanly from A to B, even on a circuit board, it becomes a massive engineering headache. And that's exactly where retimers come in. They're sort of the unsung heroes making these modern speeds even possible. Okay, so let's set the scene a bit. PCIe, PCI Express. That's the main highway inside computers, connecting your graphics card, SSDs, network cards, all that stuff. Our sources remind us it's layered, but we're focusing on the physical layer, the wires, the signals. And the big story with PCI generations, Gen 4, 5, 6, heading towards 7, is speed, speed, speed.
Right.
Now, what's interesting is PCIe uses serial links, point to point. Data goes bit by bit down dedicated wire pairs, not like older parallel stuff. This helps hit higher speeds, avoids timing issues, but boy, it puts a ton of pressure on that single path, doesn't it?
Oh, absolutely. Every little imperfection, every tiny bit of the path matters hugely at these multi-gigabit speeds. Even short distances on a PCB, going through a connector, the signal just starts to fall apart. It's constantly fighting physics.
Fighting physics. Okay, so what are the main enemies here? What makes a signal go bad?
Well, the sources list a few key ones. First up is insertion loss. Think of it like the signal just runs out of steam, its power weakens as it travels, and it's worse for the high-frequency parts of the signal, which carry the fast transitions.
Things like the skin effect, where the signal kind of rides on the surface of the copper, and losses in the circuit board material itself, the dielectric, they just sap the energy.
Yeah.
PCIe Gen 5, for instance, it has to cope with up to 36 decibels of loss.
36 dB. That sounds like a lot. How much is that, real?
It's huge. That's like losing more than 97% of the original signal power. It's incredibly weak by the time it gets to the receiver.
Wow. Okay, so it's barely a whisper. What else?
Then you've got reflections. Anytime the signal hits a change in the path, like a connector or one of those little vias connecting board layers, the electrical properties change, and some energy bounces back, like an echo.
Right.
And that echo interferes with the main signal, causing ringing, overshoot, basically distorting the shape.
Makes sense.
Then there's crosstalk. You've got all these wires packed tightly together on a board, right? Signals on one wire can kind of bleed over and induce noise onto adjacent wires. It's like trying to have a conversation next to someone else shouting.
Okay, so noise from neighbors. Exactly. And finally, a big one, jitter. This is all about timing. The edges of the signal, the transitions between zeros and ones, they don't arrive at perfectly precise moments. They wobble. Yeah, there's random jitter from just, thermal noise, unavoidable stuff, and deterministic jitter, which is caused by things like the data pattern itself or those reflections we talked about. All this timing uncertainty makes it really hard for the receiver to know the exact right instant to read the signal.
I see.
And all of this stuff, the loss, reflections, crosstalk, jitter, contributes to intersymbol interference, or ISI.
Yeah.
Basically, the signal for one bit gets smeared out in time and bleeds into the slot for the next bit.
So the bits start blurring together.
Precisely. The sources talk about it closing the data eye. If you look at the signal on a scope, a good signal has a wide-open eye shape. ISI swashes that eye shut. Eventually, the receiver just can't tell a 0 from a 1 reliably, and you get errors, bit errors.
Okay, let me try and picture this. It's like you're trying to understand someone whispering super fast from the other end of a long, echoey cave.
Yep.
While other people are also muttering nearby. And occasionally a random loud noise makes you miss a word. And their words are all slurring together anyway because of the echoes.
That's a pretty good analogy, actually. That's the kind of environment the data signal is trying to survive in. It's a tough physical reality.
So clearly just turning up the volume, just amplifying that messy signal probably isn't going to fix it, right?
Not effectively, no. Not at these speeds. You need something smarter.
Which brings us to the hero, the PCIe retimer. The sources give this formal definition: a physical layer, protocol-aware, software-transparent extension device. Okay, let's unpack that.
Right. Those terms are really key. Protocol-aware means it actually understands the PCIe physical layers language. It knows about link training, equalization, the whole negotiation process.
Right.
It's not just the dumb booster. It actively participates.
Okay, so it speaks PCIe.
Exactly. And software transparent. That's huge for designers. Your operating system, your drivers. They usually don't even know the retimer is there. The link just looks like one single, longer, reliable connection to the software. Makes things much simpler.
So it hides the complexity.
Pretty much. And what it fundamentally does is break that one long, lossy channel into two shorter, more manageable electrical segments. But the real magic, the critical part, is the full signal regeneration.
Regeneration, that sounds important.
It is. Unlike simpler devices, a retimer doesn't just amplify the incoming mess. It has complex circuits to recover the original clock timing from that messy signal, figure out the best time to sample the data, and then it generates a brand new, clean, perfectly timed copy of the data to send down the next segment.
Wow.
This is what we mean when we say it resets the jitter budget. It basically wipes the slate clean from the impairments accumulated on the first segment.
Okay, so it's like my analogy earlier.
Yeah.
The perfect listener in the middle of the noisy hallway who hears the garbled message, understands it, writes it down cleanly, and then shouts it out perfectly clearly.
That's a great way to think about it. It's not just relaying the noise, it's understanding the message despite the noise and sending a fresh, clean copy.
So how does it do that? What's inside this magic box?
Well, the sources describe this pipeline of clever processing blocks. Coming in, on the receive side, there's usually a CTLE continuous time linear equalizer. It's an analog filter that boosts the high frequencies that got weakened by insertion loss, kind of like turning up the treble.
Okay, boosting the weak parts.
Then, the core. The CDR, clock and data recovery. This is the really smart bit. It figures out the original data's timing, even with all the jitter, and uses that recovered clock to sample the data right in the sweet spot, the center of that shrinking eye. This cleans up the signal, turns it back into clean digital bits, and crucially, removes the jitter from the first segment.
That's the reset point.
That's the main reset point for jitter, yeah. Now, sometimes even after the CDR, there might be some lingering interference, maybe from reflections or crosstalk that the CTLE didn't fully handle. So often there's a DFE, decision feedback equalizer. Yeah, it's digital. It cleverly uses the bit values it has already decided on the previous zeros and ones to predict and cancel out the interference they might be causing on the current bit it's trying to decode. It's like using past information to clean up the present.
Interesting. So it looks backwards to help decode forwards.
Sort of, yeah. And then finally, before sending the regenerated signal out, there's the TX-FIR driver transmit finite impulse response. This is on the transmit side. It pre-shapes the outgoing signal. It might slightly reduce lower frequencies, de-emphasis, or give the start of transitions a little kick, pre-shoot.
They do that.
It's pre-compensating for the loss and distortion it expects the signal to encounter on the next segment of the channel. It's giving the signal a head start for the next leg of its journey.
So it's like analog boost, clock data recovery, digital cleanup, then smart pre-shaping for the next hop.
Yeah.
That is way more involved than I would have guessed.
It's sophisticated stuff, absolutely.
And that sophistication really highlights something the sources stress. The difference between a retimer and particularly a redriver. These terms get confused, but PCIe 4.0 actually defined them formally. So what's the big eye-popping difference, as they say?
Yeah, this is super important to get right. The absolute core difference is the output signal. A retimer outputs a fully regenerated, brand new signal with a clean clock. A redriver is basically just an amplifier with some basic equalization, like a CTLE. It boosts the existing signal, warts and all noise, jitter, distortion, everything gets amplified.
Okay, so retimer, clean new copy, redriver, louder, noisy copy.
Exactly. Think of the noisy hallway again. Retimer is the perfect listener repeating clearly. Redriver is just someone shouting the garbled message louder. It's louder, but still garbled.
Got it. What about other differences? Jitter.
Huge difference. Retimers, with their CDR, reset the entire jitter budget random and deterministic. Redrivers can only help attenuate some deterministic jitter, like ISI, with their CTLE, but they actually add their own random jitter because they're active devices. They don't reset the clock.
That seems critical. What else? Protocol stuff.
Yep. Retimers are protocol aware. They participate in link training. Redrivers are non-protocol aware. They're just a bump in the wire electrically. The protocol doesn't know they exist.
Okay.
Equalization in retimers is much more comprehensive. CTLE, DFE, TX, FIR, often adaptive. Redrivers mainly just have that simpler, often static CTLE. Retimers can kill crosstalk after sampling. Redrivers amplify it. Retimers also compensate for and reset timing differences between lanes, skew. Redrivers don't.
So retimers seem way more capable.
Fundamentally, yes. Retimers effectively create two distinct electrical links, resetting the loss and jitter budgets for each. Redrivers just condition the signal within one continuous link budget, and retimers usually have diagnostic features, eye monitors, pattern generators built in, which redrivers generally lack. Makes finding problems much easier.
Okay, so the message is clear. For PCIe Gen 4 speeds and definitely beyond, just amplifying with a redriver often isn't good enough. You need the intelligence and regeneration power of a retimer for longer, more complex paths.
Absolutely. They handle challenges that redrivers just aren't equipped for at these higher data rates. There are different tools for different jobs, but the demanding jobs increasingly need retimers.
So we know they're smart, they regenerate, they're protocol aware. How do they fit into the actual PCIe system? You said physical layer only.
Strictly physical layer, yes. They deal with the electrons and the timing. This is important because it means they have very low latency compared to something like a PCIe switch.
Ah, right. Switches operate higher up.
Exactly. Switches work up at the transaction layer. They have to look at packet addresses and decide where to route them. That takes time, adds latency. Retimers don't route, they just extend the physical connection, so their latency impact is minimal nanoseconds, really.
Yeah.
Critical for performance.
Okay, low latency. And you mentioned they participate in link training, the LTSSM. How does that work with a retimer in the middle? It can't just pass signals through if it's regenerating them.
Right. Correct. And this is where the two distinct segments concept really comes into play during link setup. The LTSSM, the Linked Training and Status State Machine, is how PCIe devices negotiate speed with equalization. They exchange these special signals, ordered sets like TS1 and TS2.
Right.
A retimer doesn't just forward these. It actually terminates the LTSSM communication from the device upstream, say the CPU side, and initiates a completely separate LTSSM process with the device downstream, say the GPU side.
Whoa. Okay, so it pretends to be the endpoint for one side and the start point for the other.
Basically, yes. For training purposes, it acts like an endpoint to the upstream device and like the root complex, the system controller, to the downstream device. It fully participates in all the LTSSM states, detect, polling, configuration on both sides independently.
And it negotiates speed and width for both segments.
Yep. It negotiates the optimal settings for the upstream link segment and separately negotiates the optimal settings for the downstream link segment, ensuring the overall link comes up correctly end to end.
That sounds complicated but powerful. Why is that separation so useful?
Because the physical channel before the retimer might be very different from the channel after it. Maybe one side is long PCB traces, the other is a cable. They need different equalization settings. The retimer can optimize the EQ using those CTLAD Festex FIR settings perfectly for the upstream channel and independently optimize the EQ for the downstream channel during training. A redriver can't do that. It's stuck within one link.
Ah, I see. So that independent tuning is a major advantage for handling complex paths. Makes total sense. It's not just boosting, it's intelligently managing two separate links.
Precisely.
Okay, so given this power, when do you really need one? Is this just for like supercomputers and extreme edge cases, or are they more common now?
Their use is definitely tied to the PCIe generation. For PCIe 3.0, running at 8 gigatransfers per second, well, channels were often manageable. Redrivers might have been enough sometimes, or even just careful board design. But PCIe 4.0 at 16 GTs, that was the big inflection point. Doubling the speed really cranked up the signal integrity problems. Retimers started becoming necessary for longer trace lengths. The sources mention around 9 or 10 inches on a PCB as a rough guideline, or systems using multiple connectors, riser cards, or cables. That's why the spec formally defined them then.
Right, Gen 4 was the turning point.
Then PCIe 5.0 hit 32 GTs. At that speed, that 36 dB loss budget we mentioned, it's just brutal. Retimers became pretty much critical for many, if not most, designs, unless the components were practically touching.
Okay, central for Gen 5. What about Gen 6?
PCIe 6.0 at 64 GTs introduced PM4 signaling. Instead of just 2 voltage levels for 0 and 1, it uses 4 levels. This doubles the data rate per cycle, but it creates 3 much smaller eyes in that eye diagram.
Smaller eyes. Harder to read.
Much harder, way more sensitive to noise, jitter, any imperfection. So for Gen 6, retimers are generally considered essential for almost any practical distance. You really need that clean regeneration, especially before the signal hits the forward error correction logic, which relies on a reasonably clean signal to work well.
Wow. And Gen 7?
PCIe 7.0, pushing 128 GTs, still with PM4. I mean, you're really at the bleeding edge of what copper can do electrically over any distance. Retimers will be indispensable there for electrical links.
Okay, so the need scales directly with speed. Where specifically are we finding them in systems?
all sorts of places where high speed needs to travel more than just a few inches. Server motherboards and backplanes, connecting CPUs to lots of memory, network cards, accelerators across large boards, definitely need them there. Riser cards, those cards that let you plug in expansion cards sideways or in different spots. They add trace length and connectors, often tipping the balance towards needing a retimer. Cables. This is a huge area.
Yeah.
If you want to run PCIe between boxes or even just across a rack, you need help. Retimers are built right into active electrical cables, AECs. These use copper, but have retimers in the connectors to clean up the signal, letting you go, say, up to 5 or 7 meters.
Active cables.
And for longer distances, you have active optical cables, AOCs. Here, the retimer often bridges the electrical domain on the chip side to the optical domain for transmission over fiber, then back again at the other end. These enable truly disaggregated systems.
Disaggregated, like pulling compute and memory apart.
Exactly. Putting GPUs in one box, CPUs in another, memory somewhere else. Connected by high-speed PCIe CXL links over AOCs, often using retimers. Even high-performance add-in cards themselves, think complex GPUs or network cards, might have retimers on the card if the internal routing is long or tricky. And AML infrastructure. This is a massive driver right now. Building those huge training clusters means connecting potentially thousands of GPUs together with massive bandwidth. Retimers are absolutely fundamental to making those interconnects work reliably over the necessary distances within racks and potentially between them.
Wow. So it's not just fixing a problem. It's like retimers are actually enabling these new complex system designs, like disaggregated computing and these giant AI farms.
Absolutely. They're foundational technology for where high-performance computing is going. Not just a patch, but an enabler.
Okay, talking about performance. How do you actually measure if a retimer is doing a good job? What are the key stats? And, well, what's next after we max out copper?
Good questions. Key metrics the sources highlight include latency. How much delay does the retimer add? You want this super low, especially for things like CXL built on PCIe. We're talking nanoseconds. Sources mention figures like under 10s for Gen 5, maybe under 7s for Gen 6 retimers. It's tiny, but critical.
Okay, low latency is key.
Power consumption. These things aren't passive. They do complex processing, so they draw power. In a big data center with thousands of them, it adds up. A 16-lane Gen 6 retimer might pull around 10 watts, maybe a bit less, depending on the vendor and features. So good power management features are important too.
10 watts per chip. Yeah, that adds up fast.
Then there's reach or equalization capability. Basically, how much signal loss measured in dB can the retimer overcome? This directly tells you how long or how lossy a channel it can support. You see figures like 28 dB for Gen 4, 36 dB for Gen 5, maybe over 40 dB for Gen 6 retimers. More dB means longer reach.
Got it. Higher dB is better reach.
Ultimately, you care about the bit error rate, BER. Is it actually reducing errors and making the link reliable? And finally, diagnostic capabilities. Good retimers have built-in tools, eye monitors to see signal quality internally, pattern generators for testing, ways to log link status. These are invaluable for system bring-up and debugging.
You mentioned CXL again, Compute Express Link. That's supposed to be super low latency for memory stuff, right? How do retimers fit in?
Yeah, CXL runs over the PCIe physical layer, so PCIe retimers are generally CXL compatible. CXL allows things like sharing memory pools, CXL.mem, or letting CPUs access accelerator memory coherently, CXL.cache. Latency is absolutely critical for these.
Makes sense.
Retimers are essential for enabling these CXL use cases when the memory or accelerator isn't right on the same package as the CPU. They provide that required low latency, high bandwidth physical link over the necessary distance, maybe to a memory expansion chassis or a remote accelerator shelf. Many retimer vendors specifically advertise low latency modes optimized for CXL traffic.
Okay, so they're crucial for extending CXL's reach too. Looking ahead then, PCIe 7.0 at 128 GTs, PAM4. Copper seems really stretched. What's the horizon?
Yeah, PCIe 7.0 is going to push electrical signaling over copper to its absolute limits. Sophisticated electrical retimers will be non-negotiable for almost any link beyond a few inches.
So, more retimers. But is that the end game?
Well, the really interesting development highlighted in the sources is the official move towards standardizing PCIe over optical fiber. The PCI SIG, the standards group, introduced something called an optical-aware retimer, ECN engineering change notice for PCIe 6.4 and 7.0.
Optical-aware retimer, so built to handle light.
Essentially, yes. It's defining how PCIe can run natively over fiber, and the retimer is positioned as the key bridge component. It handles the electrical to optical conversion on the transmit side and optical to electrical on the receive side, while still managing the PCIe physical layer protocol stuff.
That sounds like a major shift.
It is. Optics offers way more reach than copper, obviously, but it has its own trade-offs. Cost, power for the optical components, and the latency of those EO and OE conversions, which needs to be minimized.
So the future involves more advanced electrical retimers pushing copper to the max, and these new optical-aware retimers enabling standardized PCIe over fiber.
Exactly. We'll likely see more integration, maybe retimer functions moving closer to or even into CPUs and GPUs eventually. More specialization, like these optical types. And continued improvements in adaptive equalization and those diagnostic features to squeeze every last bit of performance and reliability out.
So this move toward optical isn't just a workaround. It's a strategic path forward for PCIe scaling.
That seems to be the industry direction, yes.
Yeah.
Standardizing the optical interface via the retimer makes it part of the ecosystem, enabling continued bandwidth growth for the most demanding applications.
Okay, let's wrap this deep dive. We started with this fundamental problem, signals degrading like crazy at high speeds inside computers.
The physics barrier.
We found the smart solution, the PCIe retimer, which doesn't just boost but fully regenerates the signal. We saw how it works internally with that whole CTLE, CDR, DFE, TSFIR pipeline.
Right, that sophisticated chain.
And critically, how different that is from a simpler redriver, which just amplifies the noise too.
Key distinction, yeah.
We explored where they're used everywhere, from servers to AI clusters to enabling new cabled and disaggregated architectures.
Becoming really indispensable.
Looked at the performance metrics like latency and reach, their role in CXL, and now this fascinating future pushing copper to its limit while simultaneously paving the way for standardized optical PCIe, again with retimers playing the crucial bridging role.
Yep, managing that transition.
So it feels like these components have gone from being helpful fixes to being absolutely critical infrastructure. They're making the speeds and the complex systems we rely on actually, well, work.
They really are. They bridge that gap between what digital applications demand in terms of speed and bandwidth and the stubborn but fascinating physical realities of moving signals around.
Which leaves us with a final thought for you, our listener, to chew on. We're seeing copper pushed to its absolute physical limits for high-speed electrical signaling. The industry is formally standardizing optical solutions managed by retimers. So how? How long before the high-speed connections inside even your more common devices start using light instead of just electrons? And these retimers become the silent, essential managers of that fundamental shift from copper to optics.